Hey everyone, my name is Jason Corso. I'm on the faculty of the College of Engineering at the University of Michigan and also the co-founder and chief scientist at Voxel 51. This video contains a presentation I delivered at the University of Pennsylvania's Asset AI Center for Safe, Explainable, and Trustworthy Systems this past fall in 2024. The presentation covers my views on the future of human and AI cooperative teaming, all the way from the foundational levels through application system decisions that must be made when developing these systems in practice. The University of Pennsylvania was kind enough to record the seminar, and I've reproduced that here for you. It just cleaned up the video to make sure that the audio was high quality and added some additional information that I could after having delivered the talk. Hope you enjoy it. If you have any follow-up questions, please provide them in the comments here, or you can find me on LinkedIn. Thanks.
All right, welcome everybody to the Asset Seminar. I'm very honored to introduce you to Professor Corso, who is Professor of Robotics, Electrical Engineering, and Computer Science at the University of Michigan. He received his PhD at Johns Hopkins with Greg Hager. He is really a Penn grandchild. Greg Hager graduated in the 80s. From the grad club and CIS in Penn. And he did a postdoc in radiology at UCLA. And he has received really several awards, including the Outstanding Achievement Award in Michigan from ECS, the NSF Career. You remember the Alpha Computer Science Study Group, he received the ARO, the Investigator Award, and the Link Foundation Fellowship. He has done also a lot of technology transition. He has dedicated several years on founding Voxel 51, which is really one of the very successful computer vision infrastructure companies. If you have been in any CVPR, you're going to see that Voxel 51 has a really prominent presence. And today he's going to talk about embeddings and oracles.
Thank you very much, Kostas. It's great to be here. Indeed, I feel like my career was it's already been a win because we sponsored the badges at CVPR last year. And like, for some reason, it was not that expensive, frankly. If you ever do a startup at Envision, sponsor the badge. Because everyone came up to us like, oh, you guys sponsored the whole conference. Amazing, right? Anyway, yeah, it's a pleasure to be here. First and foremost, I'd like to just thank my students and my collaborators. These are those subset of my working world that are represented in these slides in one way or another. Also, just like to note that I'm a pretty flexible speaker. For 5 years, when I was basically running Voxel 51, I had to give talks on the fly without any preparation at all. So you can interrupt me, we can derail, it's not a problem. I'll do my best to keep on track. And just finally, I have my LinkedIn at the bottom here in case you want to stay in touch. Over the years, I've noticed that it's really important as an expert or a technical person in the field to be a balanced voice of reason amidst a pretty noisy and murky social environment. So I post pretty avidly on LinkedIn, happy to engage, and I do try to engage with those posts. So this talk is all about safe cooperative AI at a few different levels. I think the term safe is, let's just use it loosely. We're not talking about like formal methods for proving AI in any way, but like just walking down some vectors of investigation that really were inspired from my childhood, right? Like this is just a Dolly generated image about the type of interaction or collaboration I've been dreaming about since I was a kid, probably inspired by this ad from Nintendo in 1985.
Will you be the one to witness the birth of the incredible Nintendo Entertainment System? The one to play with Rob, the extraordinary video robot, batteries not included. He helps you tackle even the toughest challenge.
Did you hear the last sentence there? He helps you tackle even the toughest challenge. Well, he didn't do that. He was pulled from production 6 months after release in the mid-'80s. And I was left with, this like 7, 8-year-old kid trying to figure out, like, what does collaboration with computer systems actually mean? What does collaboration with AI systems mean today, or robotic systems? And what we really envision, is something more like an interactive AI system, like an agentic AI, that can, for example, help someone like me who happens upon a car accident in the middle of the road in a future in which perhaps all vehicles are equipped with ultrasound probes, to then go and do diagnostic analysis on the fly with a guided system like this demo you'll see here.
The right ventricle is too much in the center for LVEF. Can you rotate the probe across the patient's chest to center the septum? Highlighted in blue. Good. There is some interference in the view. Let's try to move up one intercostal space. Let me know if you need more explanation to help with that.
This is a demo. That was me typing text into my terminal and then sending it to the TTS OpenAI API. But the idea is that if we had an AI system that could share the same perceptual space as we humans do interactively, perhaps we could augment the capabilities of those humans in a predictable, trustworthy manner that would enable us to basically work better and more effectively. And just to note, this video is from a Penn medical faculty who's in the back of the room here, Alison Pouch, who is a co-PI on a recent project of mine that's funded. So I'll get that a little bit more later. So in my group, we think of this as hybrid intelligence. And the goal is really to integrate human and AI systems in a cooperative teaming setting during the full stack, right? The full life cycle of an AI system, an AI method, all the way from what we might do at the low level with the data that we work with and the embeddings that are generated from contemporary foundation models, all the way through the mid-level, like this notion of, well, if we actually have interaction with humans, we have to treat those humans as fallible, everyday people. They may make mistakes. They are not oracles. They are hazy oracles, and the notion that we actually have to have some sentience about trusting whether or not we should trust them. And then all the way down to this applied level, which I'll loosely call AI task guidance. In the talk today, I'll walk you through each of these 3 levels, giving you some highlights over the last 15 or so years in my group, concluding with some exciting new developments. The most new stuff is on the right side there, in some sense as well. So let's take a little trip down memory lane, right? Like many of you probably know me as a vision and language person. That was how I built my early academic career. In 2008, in my career proposal, defined the problem of grounded image captioning. And I'll walk you a little bit on the journey, but if you notice, like in the world of vision and language, if you couch that in this problem of human plus AI cooperation, you can kind of see probably why I dedicated so long in my life to this problem, right? Like we were way far, it was distant future when I was starting out as faculty to think about this notion of human AI collaboration. So vision language was how we solved that. Fast forward a few years, my group had the first video captioning paper where we actually explicitly grounded the content that's in the video pixels to a structured representation, ontological representation, and then outputted templated language based on that. After a while, I recognized or realized just this notion of like loose descriptive captioning is it's very difficult to evaluate. If Chris was in the talk here, he's like a blue expert, right? Like those things have their limitations. So we moved into more of an instructional or like procedural goal-oriented video setting. And we have some of the early papers in this problem space as well. And then even started to publish in these early foundation models, what were called vision language pre-training. And around this time, 2018, things got really big. So this graph over here is like time versus data set size, right? So when I started out, we had tens of videos or images, hundreds of images. When OpenAI took over, because things got too big, I didn't have enough GPUs in my lab and so on, we had 400 million samples of image text pairs. And that's not the limit, although in the clip model, it's still relevant today, even though it's some years old now. But we're beginning to see this notion of what I think of as like functional vision and vision large language models or multimodal large language models. And if you take these foundational representations and without training them to, directly or retraining them, we can use the outputs in zero shot or few shot scenarios to build great capabilities. This here is the Florence 2 paper from Microsoft. It was one of the orals at CVPR this past June. And they're not alone. There are many papers. Even this morning, I was talking to Dinesh, same idea, right? Like, how can we use these foundation models to go and build capabilities that are functional for downstream applications without retraining? And what I think is interesting, seriously interesting about this sort of like inflection point we have in the development of this multimodal AI is that these models take pixels, basically, right? Like arbitrary views, like this data, and they embed that perceptual space, juxtaposing it with human natural language, right? There's this co-location or juxtaposition of the semantics with the perceptual space that results in these embedding spaces. Imagine each of these samples here is a 1,000 dimension clip embedding or something like that, that has so much structure, we can leverage it out of the box. And I just think this is representative of where we are in the field. And yet we understand very little about this space, about these spaces. We have no analysis tools to understand the manifold of like actual vision text pairs, if you will, or how far we've deviated from that manifold. If we want to understand noise or uncertainty about the space, we really need tools to capture that space. So one of the directions this curious embedding space or problem area that my group has been working on is to sort of walk in that direction. And so we've made a couple of discoveries in the last 6 months, even. It's a pretty new work. All of it's in review right now. And I'll just walk you through 2 of those discoveries here. So one question we initially asked is like, okay, given this, let's say call it like zero shot embedding space from some foundation model like CLIP or Dino V2 or something like that, does it tell us anything about what we should label on our data? If we want to go and train like an edge deployable small model, can we leverage these models to go and inform us about what we should label? If we were to do the status quo thing, it's about $1 per sample, depending on your company or your lab or whatever, it's plausible to do that, but it's a waste. You don't actually need to do that, right? Could we do the same or just almost as well with, say, labeling only 10% of those data? This problem is sometimes called the core set selection problem, right? So the goal here is to select a representative subset of the data to train a model with lower cost while minimally impacting the performance had we trained on the full data. And here are just some plausible core set selections, right, on that example. Core set is not a new problem. It has been studied for at least in the last 4 years, and I think it was proposed by Silvio Savarese in maybe like iClear 18. So it's relatively new problem, but the papers are in the right places. Each of these papers tends to define some sort of heuristic score on a sample level. The most interesting and the best performing one is the top one, TDDS. Which looks at the training dynamics, effectively assuming you have all the labels, which undermines the goal of the actual problem, but assuming you have all the labels, they'll train many instances of the model and then essentially compute a sample contribution to the gradient, overall of those training dynamics. Interestingly enough, though, each of these methods, except for TDDS, is outperformed by a random subset selection over the entire data set, which has me scratching my head a little bit, right? It's not easy to get papers in iClear or NeurIPS or CVPR, but your baselines are valuable, really. So this led us to kind of like redefining the core set selection problem, explicitly calling out the notion of being unlabeled. The goal here is to take an initial big N count data set of only our samples, only the media, XI, and choose a subset of it, SC, at a certain prune rate, like a 90% prune rate means we keep 10% of the data, 50% prune rate means we keep 50% of the data, such that we can minimize the expected loss over our model F, given that we train the model. Now, if you look at the expectation, you can see two major problems. One is that to actually compute any instance of that, loss over which to compute the expectation, you need the labels. Problem one. Problem two is there are a ridiculous number of combinatorial variants that you'd have to actually go through and compute that. So we can't minimize this or optimize this directly, but we, taking inspiration from the rest of the core set selection field, we have a method or a scoring function that approximates TDDS without actually doing the training dynamics that emphasizes the notion of coverage and minimum redundancy, right? So in this loose, figure here, purple points would score high because they are close to a lot of other points and not each other. Yellow ones would be kind of redundant in this approach or in this scoring function. And we actually discovered or learned that if we generate a sampler, we can compute those scores pretty efficiently. So in the order of minutes on a laptop for large data sets under a triangular distribution in each embedding dimension. So let me walk you through the algorithm, right? It's a pretty simple algorithm. So step one, so say you have big N samples over big M dimensions, you'll select a small number of dimensions, say 2 or 3. So like
When you say samples are labeled, samples are
unlabeled samples.
unlabeled.
This is strictly unlabeled in our work, yeah. So select, say, 2 dimensions over the embedding space. Assume a triangular distribution over those dimensions. Sample just 1 point along, in those two dimensions, and then find the nearest actual data sample or data point to that one that we sampled, and increase its score or modify its score based on coverage and redundancy, basically. Like increase its score for coverage unless it's close to other samples. That means it's redundant, so lower its score. And then do this many times. Our ablations suggest that 1 million times is the best sample for arbitrary size data sets. The key thing here is that it was a triangular sampler, though. Like one would assume that if you match the distribution of the actual embedding you're working with, like ResNet 18 is like inverse exponential or Gaussian distribution for clips, that would be a better sampler over the data set. Turns out it's not the case. The triangular distribution captures both the sort of tails of the distribution along with the steady points of the distribution. But ultimately, you get to this point where you have your zero-shot embeddings that are unlabeled. And then after the sampling process, you get a score over all of your samples. And you can use that score to then go and get labels on only the subset you want, right? The top N or top K that you sample, and then train models. And in fact, if you look at it, so CFAR 10, these are unlabeled, like random and Z-core. It's our method we call zero-shot core set selection. We're able to outperform random on both very small data sets, medium-sized data sets, and do almost as well as TDDS, which again assumes all the labels and does full training dynamics, can run for hours and hours and hours. Works also better than all the other methods, but I've got that already. But at scale, it's even more interesting because it seems like there's a suggestion that that this method might actually outperform even TDDS at scale on something like ImageNet. So there's this notion that some of the structure in that embedding space is able to capture information about what we should label, right? Already kind of helping the early stage data scientist, if you will. But now say we get these 10% of the data set labeled. Yeah.
What about comparing with the weakest baseline, which is to use 0% labels? By that I mean you just run a clustering label. And I say so because I think maybe we have done the experiment for CFAR, but I don't remember it. So I'll say with MNIST. With MNIST, you can get probably 97, 98% performance with a clustering label. So with no labels.
Yeah.
And in many of these methods that are based on active learning and selecting a small number of representatives or core sets, I've seen examples for data sets that the clustering algorithm did better.
Yep. So I would probably, we haven't done that experiment.
Like you usually need a minimum percentage of like 20 to 30% labels.
Yeah.
To just match the clustering label.
Yeah, yeah. In fact, actually, if you look at this number here, I think it is 94.58, is actually better than 0% pruning. Like the actual performance, if you use all the labels of CFAR 10, is worse than this case. There's some notion of noise in the data set that is probably getting at that. We haven't done the experiment specifically that you're saying, but one could probably argue that random is a decent proxy for a clustering-based approach if you have enough samples. If you have few, then maybe the clustering would be a different experiment, but happy to run it. I mean, it's, yeah.
My other question, which is very related, there was a long, huge literature in the 2000s, 2010 on doing subset selection based on clustering. For example, cluster centers can be your representatives.
Yeah.
Subspace clustering was another way of it. Sparsity type techniques, because you could use sparsity to do the selection using the data as a dictionary. So how does it compare to those?
All the reason why we need to work together more so that I can explore. I don't know the answer. We haven't done that yet. I think the difference between this method, like the key, like performance difference, if you will, between this method and more even like the GPCA type methods where you assume a specific model in each subspace, right? Like is that we are working in the embedding space, not in the sample space, not in the direct data space. This would not work in the direct data space, I don't think.
Yeah, but the modern versions all learn a manifold that maps something to a union of subspaces, and then you run the cluster.
Okay. Yeah. So it's closer then. Yeah. Moving forward, right? Like, so you have some subset of the data that you think is what we think is good, and you should train your models on. But we asked the question, like, what does this subspace or subset of the data tell us about the data set difficulty if we don't even train a model or a classifier, on it? Like, can we learn something about that just based on the relative structure of that space? And we do that by looking at individual classes themselves. In each individual class, we'll learn a per class manifold by standard, nothing special autoencoders. So we'll learn one reconstructor R for each class C, where reconstructor will take like the input embedding and then map that into some other subspace, and then be able to expand that or decode that as well. We can define a reconstruction error, delta C tick. So this is the reconstruction error with respect to C tick. That's the reconstructor on that space relative for one sample XC. That's what delta is capturing here. And so we'll do this process. So if we had 10 classes, we would learn 10 separate reconstructors. Have those. This is learned on a pretty small number of samples. So for the sake of the talk, I weave these together, but in this work, we only chose 100 labels, 100 samples per class for almost all the results we have. And we do have to assume that the expectation that like the mean sort of in-class reconstruction error is less than the mean out-of-class reconstruction error, which makes sense, but it's hard to prove given the empirical nature of the work. But it works in practice, right? So these are three different distributions, each for one of the reconstructed classes. The solid bars here are in class, the dashed bars are out of class. And you can kind of see that really there's a difference. This is like the Bayes risk that we'll never be able to get rid of, but there is sort of a difference between those class means. But the actual reconstruction errors themselves don't really tell us that much, right? Like it's just some notion of how spread out or how much noise or error there is in the space. But if you take certain ratios of those reconstruction errors, you can gain some more insights. In particular, the ratio of the within class reconstruction error for a sample to the second best one, right? That's what the denominator is, min C tick over everything but C, that error. That ratio chi acts as kind of like a probe for that sample across the data set. Again, we haven't trained a classifier yet. All we're doing is training these autoencoders. So what does that kind of mean, right? Like if chi is greater than 1 or greater than or equal to 1, kind of means that there is a second class that is confusing for this particular sample. Those samples are listed in yellow here. They would tend to be in the middle of regions. In fact, these are 10 of the I think something like 3,000 samples for the 10 CFAR 10 classes. This is actually, these yellow ones here are actually part of this class, but they're noisy down there, or difficult down there. And here, this is an intersection of 3 different classes, as an example. Whereas if that chi statistic is much less than 1, it's a strong indicator that the sample is distinct, right? So these are the purple samples, and they tend to be on the boundaries of the classes. Makes sense. Okay, what if we integrate all of those dataset sample probes into a sort of dataset determinant? So chi-var is the expectation over each of those dataset sample probes, chi on XC, over the whole dataset. When we think of this as like a dataset average classification difficulty score, again, only trained autoencoders, haven't trained classifiers. And if you plot this chi-var statistic on a simple graph where this axis is state-of-the-art, like data, OpenCV, papers with code or whatever, not our work, right? Published results for different data sets over chi-var. You can see some really interesting correlations popping out, right?
So low ratio means that 2 embeddings are about the same for 2 different subsets.
Low ratio means 2 embeddings are about the same for 2 different subsets of the data. Yes.
Okay. And here it is.
So this is just a mean over that.
Okay.
Yeah, yeah. So like MNIST, simple data set, right? Really easy. 1 minus accuracy, it's really low right here. Whereas data sets like ImageNet or Places 205, they're up to the top right of the graph, right? So again, this is just telling me or telling us, right? There's enough structure in those embedding spaces that we can go and kind of predict performance of models without actually doing the work of the training and the classifier. And if you walk that 1 step further, you can potentially drop this type of a model into a iterative process where you can kind of get a gradient on what's the best way to change my data set in order to optimize this score. Where do I need to fill in, where are the holes in my data set? Which is, in practice, one thing I've learned at my startup company is like, in academia, we download the data set and we work on the model. In the real world, you build the data set in the model. And the hard work is actually building the data set. And so this type of insight is really critical for the everyday work of AI scientists. So we wanted to study a little bit about the scaling behavior. So now the vertical axis on here is that chi-var statistic for n samples, okay? And the horizontal axis here is the number of samples we used to actually just compute chi-var. And we noticed that there is an interesting pattern over the data set, like this is just CFAR 100 and CFAR 10. And that fits actually across each of the data sets we work with that have at least 100 samples. So this ansatz here, this function, for each data set, if we fit these 3 free parameters, gamma 0, 1, and 2, we have the same structure of the graph, and yet we are able to disentangle, kind of predict how difficult the data set is at infinity samples, only given, say, 1,000 samples or 500 samples. We find that this goodness of fit is pretty high, almost 1. Is sound for any data set we've tried where this chi-var infinity is just 100 actually. So again, another insight that says like we're able to disentangle things like Bayes error and decision boundary complexity from the number of samples, right? Because in general, the wisdom and the folk wisdom is in our field, right? Like, let's just get more data. That'll help. Sometimes more data doesn't help. You need to change the underlying embedding space, for example, or the underlying representation. So as far as I know, this is the first empirical result of its kind, and hopefully it will appear sometime next year, but we'll see. We also want to study whether or not this generalizes outside of like just core.
Is there a way that this could also be used to assess how good an embedding is? Because if I have a classification accuracy on these set of features, these other set of features, I do 3 different feature extraction.
100%. The whole that's the goal, right? Like even if, as I just said, right, like you have 1 embedding, you're either adding data samples to help that embedding work better, or you have a guidance, some sort of gradient in some way. I mean, this is all very new work, but like that can push you in a direction that can say, change your model in this way because it will help. Indeed. And just, I don't have the time in this talk to go through them, but this data, this result and the other result a few slides ago works for, I believe this is on CLIP plus ResNet embeddings, but works on like Dino, across just we've tried it on a bunch of different embedding spaces. Also works across different domains. So this is a medical data set, MedMNIST, that is, these are all the image-based ones, just because that's the way our code was set up to run, but like, it's a little bit less correlation. I don't know what the actual number is, maybe like 0.6 or 0.7, but still relevant, right? So there seems to be an insight into the data set from these types of representations. So, again, in my view, to walk the line toward the future of AI, where human and computer systems are working together for the greater good, I think we need to better understand the underlying representation that we're working with. So I think that's the case. We all have other results, like we have state-of-the-art mislabel detection, like errors in your data set. We can actually predict the error rate prediction of a data set with just doing the same work. Just no time to talk about it, but we're looking at other directions in this as well. For example, that's all on image classification. What about video? Right, a lot of people in practice or in domain have large sets of video to work with, and they can't label it all. They can't work with it all. So can we select the right set of frames on which you should do the labeling? As just another example application.
Just to understand the final approach. So you have this quantity, I forgot gamma or
Chi-bar.
that is obtained from something like reconstruction errors from an autoencoder.
Essentially, yeah. Let's say ratios of them, but yeah.
And therefore, as I change and retrain the autoencoder, I get different numbers. How I can assess, we get different kind of numbers for different autoencoders for the same data.
Mm-hmm. And all this is on label data. We're now working on doing this with clustering-based data. Like, it would be great if you didn't even need those 100 labels per class. It doesn't work as well, but it works certainly better than random. So there's something there too. So if there's an interesting subspace learning type or clustering algorithm that could be useful, I think there's a good direction there. Yeah. So, I think this world of understanding embeddings, especially like, again, building on that like vision language space, is so critical that like, I kind of paused my academic career for some time to start a company. That company is Voxel 51. We build what is essentially like a VS Code. I'm sure that all the students here at least use VS Code, or like a microscope for visual AI. It is a Python library coupled with a user interface. It's a web-based user interface that has a tight stateful bridge between the two that allows you to work and ask the right sort of scientific questions about your data sets and your models and your embeddings all under one hood. We are about 45 people now. We're founded in 2018. I've been the CEO for like the first 5-6 years, salesman, HR person, so on. Now I'm the chief scientist and I'm writing papers at the company, which is actually good. We have more than 2 million installs, lighthouse customers. Like I learned that Chris Geyer, co-founder of Berkshire Grey, was at least a postdoc here, if not a PhD student. He's a PhD student, yeah. So they were one of our customers. I didn't list them there because I didn't realize that before I was talking about this before, but well, this has been a lot of fun. I've learned a lot. Happy to talk with any of you about like the experience of operating a startup, not just like being the faculty advisor of the startup. I learned a lot about myself and the business world in this process. It was great. All right, now let's move on to Hazy oracles. We're doing okay on time. In which we want to recognize that we can have this embedding space, for example, and get labels on it. Getting labels on it means we ask humans to give us the labels on them, right? So we involve the humans in some way. That is an interaction, but the humans are fallible. They make mistakes. this is all just an example. This is not real data, but like that's a mistake, that's a mistake, that's a mistake, and so on, right? Like I make a lot of mistakes, right? It's just natural to do that, right? So we wanted to ask questions like, how do we better involve the human throughout the AI stack? How do we understand or model when to trust that human input? If we don't actually model the human, then and their feedback, we have no principled way of doing that. So this is just moving in that direction. In my group about 8 years ago, we began to walk in this direction when we were building a data set for autonomous driving. So it was just this scenario in which, getting real data from autonomous vehicles is not that hard, right? Like you put the cameras, put the sensors on the vehicle, drive it around town. But most of that data is useful only for like normal driving scenarios. It's rare. It's something like 1 out of every 2 billion miles driven is there an accident. So it became known to our funders, Denso and Toyota, that like, well, we don't have enough of these like near miss cases or failure mode cases. However, there is a large amount of those on YouTube, especially from countries like Russia that don't have good auto insurance policies. Yet those are all monocular video. So in order to bridge the gap, we needed to figure out the kinematics and the dynamics of those monocular YouTube videos that had these accidents so that they could be embedded into these car simulation and AI type settings. So one method that we stumbled upon was this pose estimation method. Input bounding box around a vehicle, output a regressed set of pose vectors or posed variables. In this case, it's not sure for the overall pose if the front of the vehicle is that way or this way, right? So this is a challenge. This is not our method. Render for CNN was published like 2016 or 2015, but we noticed that it struggled in exactly the cases that we cared about, when there was cars nearby each other or there was damage to the vehicles. And so we had this idea, well, we're going to build this data set. If there was only one thing we could do to help render for CNN, what would we do? So the idea was, let's just ask the user, the human, just one question. Click on the back left wheel, click on the front right bumper, click on the top of the car or whatever, and then augment the original render for CNN model so that we can provide that guidance on the fly to turn, for example, the bimodal distribution into a unimodal or peak distribution. And we call this method click here CNN, right? Like it's like here and you embed it. It turns out that, so the original backbone for render for CNN was AlexNet, followed by some fully connected layers for regression. But ultimately, the way click here CNN tended to work, so this is like a one hot vector, which prompt or query we were giving, followed by like where they clicked and a noise function after that, ultimately seemed to work as like a spatial attention that was key to that class. And worked pretty well, actually, for the automotive cases that we cared about, increase the absolute performance by about 5-6%. My student, Ryan Zito, he works at a startup now for putting computer vision for helping elderly individuals in nursing homes. So this work stopped with him, but I had a new student start, and we began to broaden.
You had a 3D model here for the wheel or something?
No 3D model. So this method here outputs your KDOF. This is just 3 degrees of freedom of the vehicle in the bounding box. Yeah, so it's not this is
The whole vehicle.
the whole vehicle. Yeah, it's not part based or there's no 3D sensing here. The goal was to take the output here and then use that in other 3D systems. Yeah. So we began to sort of try to broaden this work and think about it a little bit more in context. We began to realize that there's this assumption that when we involve humans in these AI systems, we tend to think of the humans as oracles. In fact, when we were doing this work, we actually called, like in our notes in our meetings, we called humans the oracles because they were giving us the right answer, or we hoped that they were. But that's not always the case, right? So let's see, right? So like the oracle assumption is that all human provided information is semantically correct, unambiguous, and equally useful. In prompted inference, which is a little bit more relevant to this domain, where it's like a human in the loop, we'll set up a problem scenario where you have like your fixed input X, your image, your audio file, whatever, human prompt, the key point click, the a text string or whatever, and you have a task model, and then you're able to learn that task model based on optimizing your loss function, right? This is not new to us, right? Like prompted inference is like all over computer vision. We never really thought of it in this way as prompted inference, but I think it fits the general framework, like object tracking, video object segmentation, VQA, referring expression. When there's alignment between the prompt H and the media X in the context of the model, then it works, right? So this is a referring expression. Second hydrant works pretty well. As a human, I'm not sure if I would have said second hydrant is this one or that one back there, but that's okay. But there's often misalignment. Sometimes the left banana would be this guy instead of the actual left banana. And this happens quite more than you think. Interestingly, the way I want you to think about this is that there are actually two different sources of that misalignment. The first type of source, first source is the actual task model. This model is just not good enough. And what do we do when that happens? We just get more data, we train another model, and we hope for the best. That's the way our community works. But the second one is more reasonable to building systems that will actually work in the real world. And it's just this notion that there's incongruence between the task model and the prompt. There's a misalignment along that representation. In some sense, we're saying the conventional wisdom in our field is like, generate a better model, get more data, because that's the right way to do it. Whereas our challenge, or our thought, is that it's better to focus on better handling for that incongruence. Better alignment between the underlying task model and the way that humans prompted and interacted with is the key. In fact, if you don't remember anything from my talk, except for this red sentence right here, I would still sleep well at night. I think, because in some sense, I'm telling all of my machine learning colleagues that you're looking at the wrong problem. The right problem is down here. Think about it, right? You're fielding a system in practice. Humans will use that system. There will always be corner cases. There will always be situations in which that system will not work as well. So we need to figure out how to not necessarily wrap it with wrapper code like, say, OpenAI does right now, but instead, we need to think about mechanisms for better principled modeling of that limitation. We get a better prompt, for example, or a different prompt, for example, we might find the right banana. So the oracle assumption ignores the reality, right? Like the old man's not going to say, please get me the orange mug every time with this robot in its home. The old man's going to say, get me my mug. And the robot's, who knows, maybe there's a light here and it's changing the way the mug colors look or something like that, right? So the robot's going to have to, it might bring the wrong mug, right? So in this case, there's sort of like ambiguity between what the prompt is and what the human is. So we call this the Hazy oracle assumption, that human provided information may be incorrect, it may be ambiguous, it may be misaligned between the task model and the human features. So the robot would need to go and ask again to reprompt the user, right? And we all win. So how do we think about this problem, right? So put your brains back into the viewpoint estimation problem or pose estimation problem. This is one image from the data set that we were using in that earlier paper. This is if you can't tell, this is a motorbike that's facing away from us, slightly to the left. The input is a bounding box around that motorbike with no key point. The original error for this example from like the render for CNN method is very high. It's like 178 degrees off. Basically, it thinks the front of the bike is facing this way. If we have let's call it a gold standard key point or gold standard prompt, like the best we could do. This is what an actual oracle gave us in some sense. Our best case error is 18.5%. So like the geodesic error, given that prompt is 18.5%. Interestingly, and I think the prompt for this one is the rear bumper for some case, even though that doesn't look like a bumper to me, but that's what the gold standard was. Some key points or prompts from the user might be useful, even though they're far away from the gold standard in pixel space. Whereas other points, the red one up here, might be useless, even though it's pretty close to the gold standard key point in pixel space, right? That geodesic is actually, it's a weird, oddly structured And it has some essentially unlocking what is in the task model, right? Like that structure of the task model, how it represents. And so in some sense, any point in this green space would have led to the right answer. And so let's model this directly, right? So we have this loss L against Y, which is like the goal, like the actual ground truth pose for that object. Y hat GS is the pose we get from the gold standard key point. So this is like the best we could do, past loss, best case. This loss here, Y hat C, is the pose we get from the candidate, like the prompt from the human, basically. And we'll assume that the gold standard loss is the best case. So we wrap this with a max and a zero, just to be clear. We call this the notion of hazy loss or additional error. It's kind of like the additional error from you if we were to use Y hat C on top, the additional error on top of the gold standard error. Useful key point, hazy loss is going to be small. Useless key point, hazy loss is going to be large, right? So when that hazy loss is small, we'll go and use that human input right now to predict the answer. If the hazy loss is large, we'll probably defer and ask again for another input. There really are three elements in play when we decide whether or not we should infer or defer, right? First is model performance, the task model performance, right? Like in this particular image, it's all pink because there's no key point over the entire image space that could lead to an accurate pose. In that sense, like there's nothing we could do. There's no reason why we should ask again because anywhere we click would be wrong. This is really it. So as that loss on Y hat GS increases, in some sense, the harder this particular task is. Second element in play is what we were talking about earlier, like the prompt alignment. Like how good is the prompt? Right? The greater the difference in this hazy loss, the more value there is in asking for a new prompt. Smaller the difference, less value. But importantly, at inference time, the third element is that we don't actually have the gold standard. So we can't compute this directly. This is a big challenge for us. So what we ended up doing was dual loss additional error regression, or this is the way we talk about it. Essentially, it's a learning-based model that, given the problem setup I've just constructed, is able to estimate the expected value over that additional error, right? So ultimately, it has two pathways. One pathway is this rejection model, which we're learning here, and it's able to estimate this correctness loss, which is analogous to this probability that the seed is good or bad. And then this task model pipeline is actually estimating task model performance. We learned this across, like this is hierarchical scene classification. The method's pretty general. It works on the key point estimation and a bunch of other problems as well. Infer now if low, defer if high, right? So in some sense, we're saying, given like the earlier performance was like 90.7 average pose estimate, I think. This could only help them. Like, but we're putting the user into more labor by asking them to do more work by labeling more times for us, right? Just to give you some sense that it works pretty well. So this is a graph. So in some sense, each point on this graph is a mean AE over a whole data set. And the metric we reported in this early paper was the area under this curve. The horizontal axis here is like, what percentage of the points are we actually using to defer versus not defer? So we want to lower this score here. Random selection, flipping a coin, defer, don't defer, 1.54. Our method is able to get it to 0.28. The only baseline we're aware of is like the selective prediction work, which is analogous to this SR here. So we're able to do roughly 3 times better than like the only other standard method that we're aware of that sort of structures this problem of like infer or weight. But even more interestingly, these are the predicted geodesic surfaces of how well we'll do. These are the ground truth ones, the ones we actually sampled from data. All right, great. So moving ahead. So again, safe, trustworthy, cooperative AI demands that it's bidirectional, right? GPT should tell you, I think you're being silly. Tell me, be more serious. Well, for example, right? Like we need to have that interaction model better. We have other papers and like multiple interactions in one session. We've also begun to do work in user studies with many different types of hazy oracles and how that impacts the way we interact for things and ask for things and so on, but not much time to get to that. So let's bring it up to the AI task guidance, which is the more high level or applied work. So one project we have in the lab is the use of computer vision and these AI models to predict the performance and expected outcomes for open heart surgery. I blurred the video here for your benefit. This is an R1 project that I'm a part of, spread between Michigan, Brigham and Women's, Mayo Clinic, and so on. We have about 200 recorded cases, each about 8 hours, like really long videos. And what you see here is the output of our hand tracker on these videos. Hand tracking in this domain is very difficult because of lots of self-occlusions, lots of mess, everything looks the same, and so on. But one quick result we had in this when we first started the project was a better conditionally, like a temporally conditioned fine-grained hand pose tracker that was able to not just treat every frame separately, but input the pose from the last frame into a pose estimation network that's actually able to learn from it. And we're able to do best in class with some of these type of data. We have a new paper actually that came out at BMVC. So my group has been working a little bit on pose estimation, both for hands and full body for a while now. But we had a BMVC paper this year, which if any of you have worked in like 3D pose estimation of full human bodies, right? Like the legs are often flipping around and stuff. It's a real pain. So we have in this method, instead of using like the standard like joint errors, like Euclidean distance on where the joints are, we embed the poses into a physics simulator and compute like a scoring function based on how long the human body stays upright and things like that. So we've been looking at these types of pose estimation for a while. Oh, these are not blurred. If you don't want to see blood, just close your eyes for 2 minutes or for 20 seconds. So just to give you a sense, like this is a really hard vision problem, right? Like lots of mess. The gloves, the hands look a lot like the background, like very difficult problem. Admittedly, I haven't tried like the new things on this data, like SAM2 or other things like that. Maybe they would work pretty well to help, but I'm not convinced. So anyway, in order to build a rich enough model to go from hand tracking to like skill level prediction, we had to get a lot of data. Those videos we had just were not enough. So we went to YouTube, got a huge amount of data like you just saw there. And we trained a skill level classification network, which is able to take these types of overhead videos and we use a contrasted learning setup, right? Like where like one of these videos is a surgeon doing the work, and that surgeon has a certain skill level, years of training, right? Like if they're an attending, maybe they have 15 years. If they're a resident, maybe they have 5 years. And we use contrasted learning to group the skill levels together to ultimately predict either senior or training. And the scores for our prediction are here, right? So contrasted learning is the bottom line. Works 28.7% better than random, which is good. Kind of better than typical transformer type things you might do in the raw pixels or SVM classifiers and so on. So like the contrasted learning in this case was really helpful at the clip level. And even more interesting, we're able to use our features to provide useful insights to the surgical team to quantify like one thing they care a lot about is economy of motion, right? Like how much is the surgeon moving their hands or kind of wasting their energy? Can you imagine standing over a patient for 8 hours, right? It's a rather laborious task. And so experts tend to move their hands quite minimally, whereas novice surgeons are always moving around, often making mistakes. Although in fact, if you look at like the file size, like the file duration, that's the best classifier between novice and expert, just to give that away. Yeah. Reviewers did not tell us that when we submitted the paper. All right, so interesting. So this is like one step, right? Like if we have better models of what's happening in the real world of those humans, we can provide better guidance. And this has really been the focus, not only for training, like that sort of skill level classification, or if you will, but also for like in the loop guidance. So I'm the PI on a DARPA PGG project for the last few years, in which we tried to basically build that full system. Like imagine like you put on an HMD, there's a library of tasks that the system knows about. Then the human goes and begins such a task. We have the shared perceptual space between what the human's doing and seeing and what the computer system is doing and seeing. And the goal is to, given an existing knowledge transfer or recipe description, actually interact with the user, prompt the user when they're about to make a mistake. You know, don't use the salt, use the sugar, right? Or don't use that scalpel, use this scalpel, right? Like that kind of thing, right? So we have built, you know, I'm a builder. I build research lab, build a company. I also like building things. So we built actually three physical systems of this project. One is based on a webcam. This was used more for like the military setting when we were doing engine repair. The looking forward was more useful than looking down in that case. We built, our primary one is based on the HoloLens 2 from Microsoft, although it's now discontinued, even though it was a pretty great platform. And then our more recent one uses a Roku Air Pro. So this has like embedded computer vision in it, whereas this guy here is just like, think of it kind of like an external monitor and audio. So like you have to plug it into your computer, you can see full, you know, actually stereo vision, and you can record video and record audio. And we're working on one that uses like lighter weight glasses, like Meta Ray-Ban glasses. When I say there's a lot of engineering, I just have this slide in here as a thanks to my students, specifically Yayuana and Philippos and myself, who were in the lab writing like ZMQ code until 1 a.m. for weeks on end for DARPA, because none of this was publishable either, which is so upsetting. But anyway, we have this great software system that essentially has this conductor process, which is like the brains in some sense, right? Like we learned, the biggest learning we have from this project is that like the first thing we tried to do was let's sense everything and understand everything, kind of like the way I think most like autonomous vehicles work right now. We have to have a good ISR at any point. We found it was too hard to get that good enough in order to actually use it in real time for guidance. So what the conductor does is essentially has some knowledge about what task is happening, what step you're in, and then it provides these like instantaneous queries on the data. I should see peanut butter now. I should see a screwdriver now. If I don't, then it stops. And at some point, we use an LLM to actually govern that guidance or that interaction between the human and the user. So here's just an example in the cooking domain. What you see, so up here is the actual software system running. This string here is the output of the system. That will be large in the bottom of the screen here. This environment here is actually my lab at Michigan. It's like one of our 11 environments we worked with. The humans doing the work over here. Video will run pretty fast. And they're making a cake. Important for this DARPA project was the notion of making mistakes and tracking mistakes. So in this case, if you can see, he's actually pouring coffee beans out of this blue mug instead of water, which was the right step, right? I'll start it over again so you can kind of look, but like the system was sentient enough to recognize that you were doing step 4 instead of step 1, even though it looked like you might be doing step 1, right? So that kind of thing. And the challenge though is like, there are so many ways you can make mistakes in these types of problems, right? Like it's an open world problem. So more recent work that is in review right now is the ability to take a contextual image like this column here and a contextual sort of action description, like a step of the recipe, you know, roll the dough, crack the egg, whatever, and generate a video that's usable in training for these models. That video cannot change the background, right? The whole point is like that we need different backgrounds for the same types of actions and so on. And it has to have good fine-grained motion of the activity so that when the human's actually doing it, it'll be useful. And so this column here is state-of-the-art video generator from text. This is open source. Everyone's heard about that, and this is ours. These are admittedly cherry-picked cases. I can't show you the whole data set here, but these are pretty good, right? Like the knitting one. Okay, the first one here, there's no knitting actually happening, but it doesn't change the background. Sora gets everything wrong every time. And here, it actually looks like knitting. Like there's like sort of a sufficient signal in the video that is really encouraging for all three of the cases here. We have generalized this to battlefield medicine. things like XStat testing and chest
You
seal.
just say how you do that. So you begin, the system starts at one frame and generates a video.
Oh, well, sure. Yeah, sorry. Sometimes I get into like marking mode. And so, so it's a two-phase process. We take the input image. I think we embed both of these with clip to kind of like start. But then we unroll that embedding to first deduce a region of motion. Given the context and the action, where should it be happening? And so we have this region of motion video. And then given that, we just use like the diffusion method, but condition the diffusion not only on the text, but also on the region of motion.
And how do you ensure that the background doesn't change?
Well, we don't, given that region of motion, we don't let them, if it's not part of that mask, part of that region, we don't, we force it not to change. How do we do that explicitly? I would have to go and check with the student. I don't actually know.
The solutions I know is that you just run the full diffusion model, but then you mask at the end, and
Yeah.
you need to do some sort of blending to get it smooth.
Yeah, I don't think we did that because these are too smooth for that.
Yeah.
Let me get back to you. We applied this to battlefield medicine, same type of setting. These were all part of another DARPA performer BBN. And more interestingly for me is, so we're just beginning, we just signed the contract like 10 days ago, this new project on this type of AI task guidance for rural medicine, right? Like how can you take this is notion of like an ambulance version 2, right? Like drive it around to rural Indiana, or I guess even rural Pennsylvania. I don't know if there are any officially rural areas in Pennsylvania, but there may be. To houses, to nursing homes, to places where people cannot get the right care they need. But we don't have we can't send doctors like experts. It's just too expensive. There's too few of them. So can you use a generalist, someone with more medical training than me, but less medical training than a physician, to there? Okay, then they put on the head mounted display, or it's flat panel based, and they'll be walked through different procedures. We're beginning with like that ejection fraction estimate from earlier is one of the examples that's part of this project. We're also looking for like venous access, like tumor volume estimation and things like that. It's a pretty big team. So I'm the lead. We have a group here at Penn, Purdue, Colorado State, Northeastern, Stevens, Rochester, Central Michigan, and Raytheon. Raytheon's an integrator, and so on. So anyway, that's very exciting. And yeah, thanks for your attention. I appreciate the questions and the interest. And again, just concluding statement, key things are in red in this talk, right? Like, I think cooperative AI is almost, it's just nascent. It's like a little baby. We're only beginning to see the potential. But in order to deliver trustworthy systems that fail, when they fail, we know that they're going to fail, or that they're able to communicate that they're uncertain right now, requires that we look at these 3 different levels collectively in our research programs. So just want to acknowledge my funding sources, and most of this, if not all, is open source, and happy to take your other questions and discussion.
Thank you for the great authorization questions.
So there's a lot of questions to always, but that I like I don't know for a market that doesn't answer, like it doesn't simply go to answer something. So your work was trying to come up with better thoughts somehow. Let's see the correct answer. So my question is that when a random user asks a question, do we have any metrics for saying that the correct answer is correct? Is it possible to even do that?
Yeah, so your question is basically, right, like how user specific are the Hazy Oracle methods, or like how do these relate to LLMs, for example, right? So a couple things. I guess one is that this is all the frontier of at least my group. So we haven't bridged between Hazy Oracles and LLMs concretely yet. So that's new and ongoing work. But all of the Hazy Oracle work we have right now is not user specific. So it's all based on like the general population of data we have. So we don't have the notion of like, the Costas model versus the JSON model versus the newcomer model. I do think that's the right way to go, like to have this notion of kind of like shared almost like, in like RL and like various like robot policy learning now, you can hear this notion of like skill libraries. You can have, I anticipate a future in which there are this notion of like experience libraries, right? Like, okay, if you have Jason, well, he's a combination of like an American, a computer vision researcher, a father, right? Like, and you put those together and that's the surface of the model you use. But I think we're a pretty long way away from things like that, yeah.
Jason, the first part, I mean, the word that was coming continuously in my mind was active learning. Okay?
Yeah.
Because in active learning, you're either choosing what to label, or you're choosing a new use for camera or in measurements. So I could, can you tell us a little more how it relates to the?
Well, actually, the original course set selection paper from Silvio is an active learning paper. So it was written in the style of like, I've trained a model with this set of labeled data so far. What is the next thing, right? So what is the core set from the unlabeled data set? The community though dropped that notion as they moved into this sort of fully labeled core set. But that's why we called it the cold start problem, right? Like you can use this in active learning, I suppose, but this would be first. And we have not looked at, like, if you do want to use it in active learning, how do you do like the second Z core? I think it's a plausible direction, but we haven't done it.
It will be after that, because in active learning, you need some model to start. I mean,
Yeah, this would be the first. This is the cold start problem.
Yeah. But one could use it having frozen models come up with tasks, right? And then start using it for a downstream task,
Oh, you could, I mean,
like Dyno or.
yeah, I mean, even in this case, like, we use, that's why we call it zero shot, right? Like we do use a frozen model as the original embedding. And like I was telling to Renee before, I don't think it would work if you don't use these contemporary sort of frozen models. Yeah.
Right. Thank you again.